Hi. Okay. So yeah. So we're going to make a switch of the books, but I would recommend you going through some other books simultaneously on groups, because the preset on groups, unlike the one that we had that was for categories, is not going to be just from a Luffy or just from a single book. It's going to be from several books. I think I go from Arton primarily, but I also use Dumbit Input, Judson's Abstract Algebra, and Rotman's book on group theory. And like they're all mentioned, like which one is from which book, but it's good if you can like go through um, just a few definitions and problems from each of these books, so you can have a broader idea. But again, they cover all the concepts at the fairly equivalent level, so you're not going to find that much of a difference, except in the way they present it. So yeah. So, yeah. Hello, Ryan.
Hello.
Mm-hmm. Okay, so yeah, we got our people, and we'll start with theory. So also the other recommendation is that this is something we did when we started Abstract Algebra for the first time on the server, and we started right away from groups. So these were the lecture notes that we followed of 18701. This is taught by Michael Arson, the book that we're going to follow. So it's pretty good. Yeah, the lecture notes. You can go through them, but it's pretty much the same as the book, except it has a few more examples. But yeah. Okay, let's start right away. So groups, Arson. Okay, so we're going to again do some basics so that we can get to the definition of what a group is. But before that, we need to do some fair amount of basic work, so that like we can have the tools that we need to define a group, right? But before we do that, I think it would be better if you can like have a more intuitive idea about what a group is before we meet a formal definition. So again, the intuitive idea and the formal definition are kind of the same thing, but the intuitive idea is that you have a set and you impose a law of composition on the elements of that set, right? And we're going to see what the law of composition would look like. It's also pretty intuitive, but you impose the law of composition on this set, and together with this set and the law of composition, they will form something that we call a group. And formally, you're going to have a few more conditions uh, of like what can be a group of what and what can't be, and we're going to see that. But like intuitively, when you're thinking about a group, you're going to always think about like you have a set and you have some law of composition on it, right? So yeah, a set with law of composition. So that's the kind of intuitive idea for what a group is. But before we get there, we're going to do some basic work. One disclaimer is that I'm not going to go through the text line by line because it has a number of examples, and it has a lot of things that's is something that you can just read through on your own. So our main approach is we're going to define things and we're going to see the important proofs, and so that we can proceed. Okay. So yeah, and for those who have joined you to this time. You can speak whenever you want to. You can just jump right in, or you can say something in the chat. The Chalkboard channel is where we talk during our lecture streams. So, yeah. Okay. So what do we actually mean by law of composition? Well, it's pretty much the same as you've seen in functions, right? So when we were doing functions, we had the law of composition about among functions. When you will take two functions and then compose them, and that composition was associative and everything. And we're going to do the same, exactly the same thing here, except we're not going to just do it with functions, right? So a law of composition, what it does is that it is applied on a set, and it's a rule which takes two elements of the set and assigns something, and it is assigned, those two elements are assigned to some other element of the same set, right? So it takes two elements A and B, and it is assigned to some other element P of the same set. So you can have this kind of a map, right? From S cross X, or the Cartesian product, it takes an ordered pair of two elements, and then it maps onto another element of the same set, right? So the law of composition can be represented in a variety of ways. It depends. It's really up to your charts how you kind of define it and how you use the notation on it. But for the most part, we're going to have the definition. Sorry, the notation would be the circ, right? But here in Artin especially, he doesn't use any kind of specific notation. He just uses this AB. So when you write AB, you actually mean A composition B. So there is an implicit law of composition between these two elements, and that's how Artin denotes it, right? So yeah. Like one of the things that you probably have seen before if you've taken linear algebra, or not even linear algebra, just like determinants and matrices. You have something called the matrix multiplication, and that matrix multiplication is essentially a law of composition between two matrices, right? And if you have tried the p set one, you can relate to one of those problems which is related to matrix multiplication and something like this. So yeah. Okay, so now we're also going to say that this this multiplicative notation, or like this law of composition, is actually associative. So what this means is that you can have the law of composition applied to three elements, and then you can like essentially move around the parentheses as you want. So AB composed first, and then composition C, it's the same as A composition B and C composed together, right? So it's associative. So then if you can also like have the law of composition to work in the either direction. So if you have like A composition B is equal to B composition A, then you have it as commutative, right? So one of the examples is that addition on natural numbers is commutative, right? So 2 plus 3 is equal to 3 plus 2. So that's the law of composition. And here you might really see that like this law of composition, which looks like a quote-unquote product, isn't really product in the way you would think, like 3 multiplied by 2. That's not really the product. It's kind of like a more abstract format of like having a composition between two elements, right? So A plus B is actually composition of two elements, right? So yeah. So yeah, the thing is that the associative law is actually more fundamental than the commutative law, because the thing is the commutative law is actually something kind of special. It's like it appears only in specific cases. We will see those would be the commutative groups, or called the abelian groups. But as of now, we're going to show like how the associative law is actually more like stronger, right? So they do this using this way, which is kind of important. So we'll go through this. What you have is you have a set, and you have two maps, a G and F, which go from T to T. Then you have the composition of these two maps, that is G, circ, F, right? So it's the composition map, which takes you from the T element to G of F of T, right? That's the composition. So this is, first apply F on T and then apply G on F of T, right? So, the rule which takes two functions, two maps from T to T, and then gives you a composition of these two functions is a law of composition, right? So it's a law of composition on maps, specifically law of composition on maps which go from T onto itself, right? And this law is associative, right? So if you take three maps that go from T to T, you compose them using this composition of maps, like, it doesn't matter how we put the parentheses, so they're associative. Okay, so that's how the associativity works. But here we're going to see something more specific. So here, we're going to see how the commutative property needs some more information. So essentially, the thing is, the associative law doesn't need anything other than like two maps, three maps, and the composition with it. But the commutative is going to need some more for it. So okay, so let's say the set T actually has two elements, A and B, and there are four maps that go from T to T, right? So we're actually going to like meet each of these maps in different formats. We're going to have like specific names to them in groups, but here we see them in terms of maps. So you have I, which is the identity map, which is defined as I of A is equal to A, and I of B is equal to B, so it gives you the same thing back. Then you have the tau, which is this transposition map. So what it does is tau of A gives you B, and tau of B gives you A, right? And then you have the alpha, which is the constant function, which like always gives you a single constant element back. So alpha of A is equal to alpha of B is equal to A. So for any value, it gives you A. And then you have the beta, which is also the constant function, which gives you B all the time. So beta of A is equal to beta of B is equal to B. So what you do is, now you have a set of these maps, right? And now you try to apply the law of composition onto this set. So now you're trying to have some kind of composition between these maps. And how you do that is by making a table, right? So a table of kind of like multiplication of these maps. So what you do is you have I, tau, alpha, beta, I, tau, alpha, beta on each of the sides. So you take the composition of I and I, you get I back. So the identity map, composition identity map, is going to just give you the identity. So, but when you take the composition of I with tau, the transposition map, you're going to get the transposition map, because it's the identity map. It's going to give you the exact same thing which you compose it with. So this first row is going to be exactly the same as this, because you're multiplying with the identity map. The transposition map, now this is where it gets interesting. So transposition is going to give you the alternative, right? It's going to just change the orders. So tau composition sorry, tau composition I is going to give you tau, right? Because that's what the transposition does. Tau of A gives you B, and tau of B gives you A. So then if you take tau of tau, so tau composition tau, you're going to get back I, right? Because it's the reverse order. right? So this is going to be tau I, then instead of alpha you're going to have beta, and then alpha. So, and in this manner you make the composition, and these two you can see pretty trivially that they're going to be the same because they are the constant functions. They give you the same thing no matter what you apply them with, right? So yeah. Also yeah, hello Brian. Okay, so there's some tremendous amount of noise from your side. I hope you get that fixed somehow. Okay, so this was the table for the composition of maps, and we will actually not need this most of the time because this is kind of mostly trivial. But when you're trying to first learn how to compose things, this is a good way to make a table. All right. Okay, so now we have a few propositions. We'll go through them. We'll go through their proofs, and then we'll be able to define what a group is, what a subgroup is, and then a few properties of them. Right. Okay. So yeah, so we have the following proposition, which says that you have an associative law of composition on a set S, and there is a unique way to define for each integer n a product of n elements from this set S. So right, so you have like the set, then using this composition, what you can do is you can like have a product of n elements from this set, and then you can have the product, so a1 till an. And how you denote the product is by this. You like write them within closed brackets, right? And they say that this product has some following properties. So the properties are that the product a1 in the closed brackets is just the element itself. So the product with itself gives you back the element. Um, you can hear me, right? Okay. I thought I got disconnected. You can hear me, right?
Yeah.
Okay, cool. So yeah, so this product, this is just like some, like defining some basic things, what you can do with the product. So the product must satisfy that when it's taken with itself, it gives the same element. When you take two elements, it's just the law of composition applied. And then for any integer I between 1 and n, the composition, the product, this product that we just defined, is equal to a1 till ai, composition ai plus 1 till an. So essentially you can like break things, right? So if you have like a1 till a3, so a1, a2, a3 within this closed brackets, you can have you can write that as a1 till a2 and then just a3 itself. Right? So that's what it is saying. So the proof of this is using induction. And if you're familiar with proof writing, you all of course know what an induction is. Essentially, you start with some value of n, and then you say that we assume that it works until um, k value. Then you're going to claim that it's also going to work for k plus 1. We're going to show that. So and if you can show that, then it works for every n. So that's the induction. So how we do that? Let's see. Right. So here's the thing. From 1 and 2, how you define the properties, these properties. For 3, when n is equal to 2, it just is the same thing as the property 2, right? And using property 1. So that's the one that no, that's not the one that I showed, but it's like if you have a1 and a2 in the closed brackets, then you can just write a1 close brackets with a2 close brackets, right? So that's using the property number 1 and the property number 2. Okay, so that's so we kind of start from there. So now we suppose that we've defined this product for R elements, right? So R is actually less than n minus 1. Because we want it to work for n, so we want first of all it to work for like at least n minus 1 elements. So we assume that like it works for our elements, and it is unique. It is a unique product that satisfies the properties. So then what we do is we define the product of n elements by this rule, right? So a1 till an is equal to a1 till an minus 1 with an, right? It is just using the property 3. Right, so if a product that satisfies 3 exists, then this formula gives you the product itself because of like the property 3. You take I equals to n minus 1, you're going to get exactly this formula, right? So if the product of n elements exists, it has to be unique, right? And okay, right. Yeah, right. So now what you do is you check for the um, you check for the all the i's that can work that are less than n minus 1. So what you do is you start from the formula that we just got to, that is this. That's our definition, and then you apply the induction hypothesis that it works for i's that are less than n minus 1. So the product of a1 till ai with ay plus 1 till an minus 1, and then you have a n. So this is applying again property 3 for I that is less than n minus 1. Then what you do is use the associative law to move the parentheses, and what you will get is precisely this. And so a1 till ai, then ai plus 1 till an, and this works because of this. This is just ai plus 1 with an because of the formula that we define. So and that completes the proof that this is actually a product. And yeah, and the thing is, you don't really need these brackets to be within them, so that's what Artin does. He removes the brackets, so whenever you have this as a sequence, it's not really a sequence, it's a product of n elements, right? Okay, so yeah, any questions? Hello, Calvin. Okay then, so we're going to
Oh, sorry.
yeah.
I just came to check how stream's going. So just can I be on the background?
Sure,
Can
sure,
I
sure.
stay?
Yeah.
Okay. Thank you.
So now we're going to define the identity for a law of composition, right? So now this is not going to be an identity map, it's going to be an element actually. So this is where we get closer to having a group. What you have is an identity for a law of composition is an element E of S such that when you apply the law of composition with that element to any other element, you always get back the same element. So E composition A gives you A for all the A's in the set, right? And it also works in the opposite direction. So A composition E always gives you A. So that's the identity. And of course, if you've seen this, the multiplicative identity, that is the multiplication on integers, the multiplicative identity is 1, right? So any number times 1 gives you the same number. So that's the identity. And the special thing about the identity is that it is unique for the entire set. So for the entire set of integers, you have one multiplicative identity, and you have one additive identity, that is 0 and 1. So that's what makes it special. The identity is unique. Hello, JPA.
Hey there.
Glad to have you
here. I'm like.
Yeah, we just defined the law of composition. We're just doing some basic stuff until we get to groups. Okay, so you can try to prove this. This is pretty easy. If the identity is actually unique or not, you do that with contradiction. You assume that there are two identities, then you apply the definition of the identity, then you realize that the two identities actually have to be equal, and that's what they do in this one line. Okay, so yeah, so both matrix multiplication and the composition of functions have an identity, right? So you've seen this. If you've done linear algebra, you have the identity matrix, of course, and it looks pretty interesting, right? The identity matrix with the diagonals with 1, and so that's how you have an identity for a law of composition. And yeah, a word of notation is that almost always the identity element is either denoted with E or with the number 1, right? So the number 1 here is actually a symbol. It has nothing to do with the number itself, because we're not dealing with the set of integers or the set of natural numbers. We denote that for like the identity element itself. So yeah. Okay, so we have a few other things related to this, which is also similar to what we've seen before, inverses of functions. So if you have a law of composition, it is associative and it has an identity element, 1. Then you take an element A of the set and you say that it's invertible if there is another element B such that when you compose these two elements A and B, you get the identity, right? So this is again something very obvious, like in terms of like multiplicative inverses, you have the reciprocals. So you have x times 1 over x gives you 1, right? That's the logic here. So when you take two elements of the set, you apply the law of composition, you get the identity back, and B would be called the inverse of A, and A as an element would be called invertible if such a B exists, right? Yeah, and the inverse of an element, just like in functions, it is denoted in this manner, a to the power minus 1. Okay, so yeah, we have a few properties of these inverses, as we've seen in functions as well. So you have the left inverse, the right inverse. So if an element has both left and right inverses, then it is invertible, and the left and right inverses are actually equal. L is equal to R, and R is the inverse of the element A itself. So that's kind of the basic idea which you've seen in functions. Then if A is invertible, then its inverse, if it exists, is unique, right? then if inverses multiply in the opposite order, right? So if you have A and B are invertible, then the product AB and the product AB taken inverse. So now you're taking the inverse of the AB, not A and B. So the inverse of AB is going to be B, inverse of B, composition inverse of A, right? And this is kind of very helpful when you're dealing with inverses and compositions, and it changes the order of the multiplication. Okay, so yeah, the last one is that an element A may have a left inverse or a right inverse without it itself being invertible, right? So you can have like either left or right, but when you have both of them, then it is only invertible. And again, a word of notation: when you do repeatedly apply the law of composition on the same element, you can have the power notation, right? So if you have like a to the power n, is going to imply a the law of composition applied on a n times, right? And that's the power notation. Is going to be incredibly useful when we deal with free groups and stuff, but that's much later. Yeah. Hello, Mika.
Hello, Divya. Hello, everyone.
Okay, so finally we get to define what a group is, and here we go. So a group, as I said before, I encouraged you to think about it intuitively in this manner, that a group is a set G and has a law of composition, but I didn't say about the following properties of the law of composition, right? So it has these properties. The law of composition is associative, alright, and that the set G contains an identity element for this law of composition such that it acts as an identity for any element in the set. So one composition, any element, is going to give you the same element back, right? And the third condition is that every element A of G must have an inverse, right? So such that, like, A composition B will give you the identity, and same the other way around. So this is what a group is, right? Like right away you can like think of many groups which you've met before, right? So Z, the integers with the addition on them is a group. Same for rational numbers, real numbers, right? So this is the definition of what a group is. And when this law of composition is commutative, right? This is what I was saying when I was saying the commutative property is actually more special, right? So it acts on very specific cases. So when this law of composition is commutative, this group that you have this law of composition on is going to be an abelian group, named after the genius mathematician Niels Henrik Abel, right? Okay, so yeah, any questions? Okay, then move on. So yeah, you have some basic examples. The set of non-zero real numbers is an abelian group under multiplication, right? So if you have two real numbers, p and q, you can like the multiplication on those two real numbers is independent of the order, right? So pq is equal to qp. Okay, so the set of invertible n cross n matrices. So this is interesting. So we're going to meet this later, but the set of invertible n cross n matrices, you might have seen this before if you've taken linear algebra, but it's the special kind of matrices, right? So they are the square matrices and they're invertible, and they together form this very special thing called the general linear group. We're going to see this in a minute, But so this is like one of the examples of what a group can be, and under this group you have the composition, law of composition of is the matrix multiplication, right? And as you can imagine, this is not abelian because matrix multiplication is not abelian. Right? Okay, so now we have some more definitions regarding groups. So you have the order of a group is just the cardinality of the group, so it's the number of elements that it contains. So it's just the number of elements of the underlying set of the group. So if this order is finite, then the group is finite. If it is not, then it's an infinite group, as it is used for like sets. So yeah, this is again a word of notation because this can actually easily get confusing. So z with plus over it means the set of integers with the addition as its law of composition, right? So it's the additive group of integers. It can be similar to imagine that z plus is actually the like set of positive integers. No, it's not. It's integers with addition with them. So it also includes a lot of negative integers, of course. The same for the real numbers, right? So this is the additive group of real numbers, and this is the multiplicative group of real numbers, right? And the same for the complex numbers as well. But yeah, so again, this is the same warning as I was talking about. R plus can denote the set positive real numbers, but it's like it is almost always explicitly denoted. But R plus here we're going to mean as the additive group of real numbers. Okay. So now we have the cancellation law. And we'll see a few interesting things about groups, the symmetric group, and then we'll see a few examples of that as well. Okay. So this is a proposition, but it's actually a law on groups. So if you have three elements of a group, and the law of composition is written multiplicatively, right? So if AB is equal to AC, or if BA is equal to CA, then B is equal to C, right? So this is actually the law itself. So you can like this is kind of like very trivial for those who are like coming like out of like no idea about abstraction, like AB equals to AC. If you just do simple like high school algebra, like A cancels out on both sides, you have B equals to C. But that's actually more subtle than that. So but instead of like having B or C, if you have just the same element, so AB equals to A, or if B is equal to A, then B has to be the identity of the group, right? And the proof is, of course, one-liner. If you what you do is you multiply the two sides of this equation by the inverse of A, because the inverse exists, because it is an element of the group. So you multiply A inverse on both the sides. So A inverse with A composition is going to give you the identity, and then the identity with B is going to just give you B itself. The same on the other side is going to give you C, so B is equal to C. That's the same thing. But what's important is this cancellation law gets more interesting when the group is has more than just some random elements in it. Okay. And here we have some interesting examples of where this cancellation law doesn't hold. Like when the element A is not invertible, right? So you cannot multiply with this A inverse because it does not have an inverse, right? So for example, if you have these two matrices, 1, 1, and 1, 1, 2, you apply the matrix multiplication. Like that's like this matrix multiplication is going to give you the same product as this is going to give you, right? But like unlike here, B is not equal to C. So if you have AB and AC, these two are not equal. So essentially, you cannot cancel them on both the sides. Okay, so now as I was talking before about the general linear group, so here we have it, the n by n matrices. So the n cross n general linear group is the group of all invertible n by n matrices, right? So this is denoted by GLN. You're going to meet this in a bunch of areas. In Lie groups, you have this, and in a lot of areas as well, because it lets you do a lot of things. So GLN is the set of all invertible n by n matrices A, right? And you can denote this GLN on specific matrices. So if you have GLN over R, that means all your matrices contain only real numbers, so they are real matrices. You can have that with complex numbers as well. So let me see. I think the notes had actually a more interesting description of the general linear group, if I remember. Okay. Yeah, it's the same thing, but except here they try to actually go back to linear algebra. So if you have taken linear algebra, you know the elementary matrices, row reduction and all that stuff. How many matrices do you need to get onto the finally row reduced form of the matrix. Those are the elementary matrices, and you can have the general linear group with those things. Okay, we don't think we'll go much into that. Okay, so this is the general linear group. Yeah, and I guess if you know invertible matrices, you know that they are linear maps, right? If you know linear algebra, you know how to think about those things, but here they don't go as much into detail, because if you want to know more about this, you should check out chapter 1 of this book. They have the this thing is explained very well there. Okay, so yeah, so now we have another interesting group called the Symmetric Group. This is also something you'll meet a lot of times. So if M is a set of maps from T to itself, so all the maps in the set M go from T to T. We'll see later these would be called the automorphisms, but here they're just maps onto itself. And this map has an inverse function if and only if it is bijective, right? So in which case we say that F is a permutation of T, right? So these maps are they're kind of allow you to have permutation among the elements of these sets. If you know about permutations, about how to arrange objects, and you might as well know the formula for the permutation and the combination, which I think it's taught in high school. So here we have these maps are permutations if they are bijective and they have inverses. So the permutations of T actually together form a group along with the law of composition for maps, right? And so these together are going to form a group, and this group is something special. So let's see. So the group of permutations of the set of indices 1, 2 till n is called the symmetric group and is denoted by Sn. Right, so this Sn is contains these indices. Right, so indices in the sense they're natural numbers, right? What this allows you to do is you can have different permutations of these indices using the law of composition, right, on the permutations. And as you can like trivially guess, there are going to be n factorial permutations of a set which has n elements in it, right? So if we have 3 elements in it, there are going to be 6 permutations, right? And yeah, indeed. So the symmetric group Sn is a finite group and it has an order of n factorial. Yep. Okay, so we're going to see some interesting things about the symmetric group. So yeah, let's see. Okay. So we start with 2 elements. You have a set with 2 elements A and B, and if you try to like have the set of permutations for these 2 elements, you're going to have just 2 maps, right? The 2 maps would be the identity map, which is going to map you back to the same element. So I of A gives you A and I of B gives you B, and you'll have the transposition map tau. So tau of A will give you B and tau of B is going to give you A. So that's these tau and I are going to be the 2 permutations for this set AB. So this they form together a group of order 2, right? Yeah, so essentially if you can replace the elements of this set AB with just indices 1 and 2, you're going to see that they're going to have the same permutations, right? So you'll be allowed to do I and you'll be allowed to do tau, and they together they are going to form a group of order 2, and that will be S2, right? So that is going to be this symmetric group of 2 indices, right? 2 elements. Okay. And yeah, so there is essentially one group G which has order 2. That's kind of straightforward. Yep. What you can do is like, you know, as we've seen before, you can draw the table of multiplication. You can write the elements. You can like compose them with the law of composition. That's multiplication, and then you're going to see that you know it's going to contain something. So let's see. So like, right, the one of the elements of this group has to be the identity, right? So now let the other element be G. So you have just 1 and G. Now the multiplication table for these 2 elements is going to give you 1 multiplied by 1, then 1 multiplied by G, then G multiplied by 1, and then G multiplied by itself. So that's how you write the multiplication table. And everything else, like, you know, composition 1, we know that they are 2, and they both are the identity elements, so that will be just 1. 1G will be G and G1 will be G, because again 1 is the identity. But G and G, we don't know what that would be like. But again, we know the cancellation law, right? We know that like G composition G cannot give you back G, right? So G composition G cannot like give you the same thing, right? But as the group contains only one and G. So if it's not G, then it has to be 1. So G, composition G will be 1. And thus, your multiplication table is defined for all the elements of this group, right? So that was for 2 elements. Now, as you go like for higher and higher elements, it is going to be more and more complicated, because you'll have to take care about like how you do the multiplication. But we'll see for S3. And this, as you can like already guess, it is going to have the order of 6 of the group, 3 factorial. So S3 is the smallest group that is whose law of composition is not commutative, because S2 is commutative. Yep. But like after this, after S3, you're going to have S4, which would be commutative, and so on. But S3 is not commutative. So let's see. And here we're going to meet some more things about this symmetric group, which would be cyclic permutations. And this is not too confusing as well, but let's see. So like in S2 we saw 2 permutations, right? That was the identity and the transposition. But here you're going to have this cyclic permutation. So how you denote that is you like write within parentheses all the elements that are going to be applied for the permutation. So you have 1, 2, 3. So what this does is it like cycles through each of the elements, and it picks up one of those, and then it repeats. So okay, we'll see that. But so that's one of the permutations that you have. So that's a cyclic permutation of 1, 2, 3, and then you have the transposition, right? So transposition, as you can guess, is just the cyclic permutation with 2 elements, right? Because as you can see, like the transposition, what it does is it takes tau of A, it takes it to B, and tau of B to A. So it's the cycle, but just consisting of 2 elements. So A goes to B, and then B comes back to A. Okay. Except in terms of 3 elements, it's not entirely obvious how that is. But yeah, so you go from 1 to 2, then 2 to 3, then 3 back to 1, and then you repeat it. So that's how the permutation works. Okay, so now we try to see the rules that we need for it to be a group. So x cubed, that is x composition x applied 3 times is going to give you the identity. And so any element that you repeat 3 times is going to be back at 1, the identity. And then y repeated itself twice is going to also give you identity. This is directly from this here. G gives you 1. So y with y is also going to give you 1. But y with x is not going to be xy or anything else. It's going to be x squared y. Right? So it's going to be x composition x, then composition y. Right? And you can check that these indeed are verified. And it's simply like applying the definition of the cyclic permutation and the transposition. Right? Okay. So so now what we see is that you apply the cancellation law onto these things, and now what you're going to get, that you have the 6 elements that you need for S3. So they are 1, the identity course. You're always going to have it. Then you have x. Then you have x squared, y, xy, x squared y. You must note that xy is not the same as yx. That's why yx is different. That's x squared y here. But xy is something else. So these 6 elements, they are going to like make up S3, which is something that's pretty useful in most of the cases, the cyclic group. So yeah, and you can see that yx is not equal to xy, so it's not commutative.
A quick question.
Yep.
Can you, maybe I just don't see it, but how exactly does the cancellation law allow you to show that all 6 elements are distinct? I mean, I know how you could like just like run work show it by checking all the different elements, 1, 2, 3, but it seems like this cancellation law that I just don't see. So.
Yeah, it's the same way you did it here, except with this way. So for example, you again have the multiplication table, you have the elements themselves, the 3 elements, 1, 2, 3, and 1, 2, 3, and 1, 2, 3 on the 2 sides, and then what you're going to do is your permutations, the law of composition, is going to allow you to do 2 things. It's going to allow you to have the cyclic permutation of 3 elements, 1, 2, 3, and you're going to have transposition. Right? So essentially, you're going to exchange either 3 elements at once, or you're going to exchange 2 elements at once. So what that will lead is that here's the thing. 1 with itself, like here, is just going to give you 1. So 1 comes back here, the identity. Then 1 with any other element is going to give you the same element back. So here you have to remember that these xy's are not any elements. They represent the cyclic permutation and the transposition. So x is the cyclic permutation of 3 elements, and y is the cyclic permutation of 2 elements, right? The transposition. So 1 with x is always going to give you x itself. So no matter like how you do the cyclic permutation of 3 elements, if you have it with identity, it's going to give you the same thing. So x comes back. Now you check for x composition x, right? Like G, you have x composition x, so that's x squared, and that wait. Now, yeah, x squared is now cannot be x, right? Just how G cannot be G, x squared cannot be x, and wait.
Share a thought on that?
Sorry?
Say, can I share a thought on that?
Wait a second. Okay, so let's see. X squared, of course, is just the cyclic permutation applied twice. So you go from 1 to 2, 2 to 3, then 3 to 1, and then you repeat it twice.
I see how they're distinct. I just don't see how the cancellation law can be used, if I understand the cancellation law properly. Unless you were looking at the converse of the cancellation law, which says that if B does not equal C, then AB does not equal AC. But I don't know. Maybe I'm just missing something for you.
I think the cancellation would be if x were equal to x squared, then by cancellation, x would have to equal 1. And that's not true.
Yeah.
So x can't equal xy, because if you canceled x, then y would have to equal 1. So I think that's what he means when he's using cancellation to argue that they're distinct.
Ah, okay. That's helpful. Thank you.
Yeah, it's kind of like, just the cancellation law is essentially like if you have like AB and AC, so essentially you have A and you multiply A with two distinct elements, and if you have the product of them is equal, then like those elements that you're multiplying the element A with are going to be equal, so B is equal to C. So that's here he like uses the cancellation law to say that they cannot be equal, so they cannot be the same elements that are multiplied, so B is not equal to C. And thus he gets 6 distinct elements for the S3.
Yeah, I think that makes sense. Thank you.
Yeah, I think like there was some interesting explanation for this. I'm pretty much forgetting. Yeah, I'm not sure if they do it here. I think they're going to put this in the exercises, but it's a pretty good exercise to play with these cyclic permutations. For example, if you see the lecture notes, like P is a permutation in S5. So what it does, it takes this cyclic permutation 1, 2, 3, 4, 5, 2, 3, 5, 4, 1, 2, right? So it's a permutation which does that. So what you can do is you can like play around like how this permutation works, like making arrows like from 1 to 2, 2 to 3, and making cycles, and that'll make a lot more sense. Okay. So that was the symmetric group. And yeah, so like what the main goal is, you write the multiplication table for these symmetric groups, and these multiplication table are going to like give you the they define how each element is going to have a composition with the other element, right? And they cover it later in like the other chapter on group theory, the more advanced chapter, which is something that we'll encounter on our 4th week of group theory. So yeah, and yeah, as I said, SN becomes very easily complicated. Like making these multiplication tables is almost impossible, like for even like S10. But until S5 is kind of like interesting. I can like play around with it, but then it gets hard. Okay, so now we have something more about groups. So now what you have is you have a subgroup. So that's something equivalent to subsets in sets. So a subgroup is a subset H of a group which also satisfies the law of composition from the parent group. So the subset H of a group is going to be a subgroup if it has these properties, which are that it admits closure, right? So if A and B are in H, then AB is also in H, right? And it has an identity and it has an inverse, just like just like how any other group works, right? So yeah, and as I was saying, the subgroup actually inherits the group structure from the parent group. So that's why this law of composition that you define on this subgroup is an induced one from the parent group. And yeah, if your group G is associative, then the law of composition is also going to be carried over to the subgroup. And yeah. And okay, so these are like examples of not examples, but yeah, kind of like main examples of subgroups. So if you know linear algebra again, um, you'll have the upper triangular matrices, so okay, so if you have the set T, which are like the real upper triangular matrices of 2 by 2, then that is going to be a subgroup of the general linear group of 2 by 2 matrices. Right? And this says something about a GL. Actually, the GL, general linear group, is actually the biggest group you can have containing these invertible matrices of a specific order. Right? So any like yeah, it contains a lot of subgroups which are important, and we're going to see some of them, but we will not see a lot of them because we're not going to do linear algebra. But yeah. Okay, so now we have a few more examples. The set of complex numbers of absolute value 1, right? That is the set of points on the unit circle in the complex plane. It's a subgroup of the multiplicative group C with the multiplication. So you have the complex numbers with the multiplication, and then you have the set of points which are on the complex unit circle, right? And that is a subgroup of this multiplicative group, and that's called the circle group. And then here, as I was saying, the general linear group has some special subgroups. Here is one of the special subgroups, is the special linear group, right? So the group of real n by n matrices whose determinants is 1, right? So you know what it means to have a determinant to be 1. That is going to be a subgroup of the general linear group. And this is the special linear group, and it is also quite interesting, though we might not need much of that. Okay, and of course, as you can guess, every group G has its the obvious subgroups, which is the group G itself is a subgroup of the same group, and the trivial subgroup which contains just the identity element. So that's a trivial subgroup. And a subgroup is a proper one if it's not one of these. So if it's not one of these obvious ones, which is like applicable for every group, then it's actually a proper subgroup. So now we are on the last section for today, subgroups for the additive integers. So we're going to see how subgroups work with the integers under addition. Any questions? I feel like the general linear group, we should like see more about it. Let me see. Right, so you can see like these are the definitions in this book are very detailed rather than Artin. This is Rotman's Introduction to Theory of Groups. Yeah, it's pretty long, but and it covers a lot of things in group theory that are very advanced and which we won't cover, but it covers them in detail. I'm seeing if they have something about the general linear group. They probably do. Anyways, yeah. Okay, let us get back to our additive groups. Okay, so now we're going to see the groups under of integers under addition. So a subgroup of this additive group of integers is going to satisfy these conditions. It must be closure. It must satisfy closure property. So that means if you take two elements, then a plus b is going to be also an element in the same set. And then there you have the identity element. So here the additive identity, of course, is 0. Then you have the inverses, of course, and that is minus of a. So here's one of the subgroups. Let's see. So we denote the subset Z that consists of all the multiples of A by ZA, right? So ZA is a set containing all the integers that are multiples of A, right? So n equals to Ka for some integer K, and this is this satisfies the closure property. So if you take any two elements in here and you add them, there's also going to be an integer. You have the identity 0 in it, and the inverses are also the same. So it's a group, it's a subgroup of Z plus. So now, yeah, we have a theorem about this, which is pretty interesting. Let's see. So S is a subgroup of the additive group Z plus. So either S is the trivial group, a trivial subgroup, so that's just the identity, just 0, or this subgroup has the form ZA. So it's a subgroup containing some and containing all the multiples for some integer A, and here the integer A is actually the smallest positive integer of S, right? So so the claim is that if S is a subgroup of this additive group, then either S is the trivial subgroup or it is of the form ZA, right? And A is the smallest positive integer, whatever, right? And the theorem is pretty detailed, and we'll go through it bit by bit. But the idea is that you can form like any subgroup of the additive group is going to be a subgroup which has multiples for the smallest positive integer. Okay, so yeah, we assume S as a subgroup, Z plus, cool. 0 is an S, yep. And if 0 is the only element of S, then S is the trivial subgroup, of course. So that case is settled. Otherwise, if that's not the case, then A contains an integer n, which is different from 0, so it has like more elements than the identity. And either n or minus n is going to be positive, right? So if you have an integer that is different from the identity, then either that integer itself is going to be positive, or its inverse, additive inverse, is going to be positive. So either n is going to be positive, minus n is going to be positive. That makes sense. So if minus 3 is the element integer, then minus 3 is not positive, but minus of minus 3, that is 3, is positive. The third property of a subgroup tells us that minus n is an S. So in either case, S contains a positive integer. Yeah. So we have to show that S is equal to ZA when A is the smallest positive integer in S. Right? There are a number of ways to do this. Kind of a more advanced way is trying to have an isomorphism between this, and you really don't need that. And we haven't touched isomorphisms yet. We're going to touch it the day after tomorrow on the next lecture. But here we go with kind of like a very elementary way. So first we show that ZA is a subset of S. Then we show that S is also a subset of ZA, and if you can show that they're subsets of each other, then they have to be the same set. Right. So okay, so what we start with showing that ZA is a subset of S. So let's see. If K is a positive integer, right, then Ka is equal to A added K times, right? That's Ka. But as A is already in S, we can show by repeatedly applying the law of composition and applying the closure property of the subgroups that Ka, that is A K times applied the composition, is also in S. So Ka is also in S. But since by definition of subgroup the inverses are also going to be in S, the subgroups of minus K is also in S. Finally, we can confirm that identity applied to the elements is also valid. So ZA, that is the set of multiples of the smallest positive integer, is a subset of S, right? We are going to look this from a categorical perspective. At least the P set will force you to do that, because the P set contains some exercises from Alufy's chapter of groups, and he has some categorical perspective on this. We'll try to do this in the second week of group theory, but yeah. Though not much, because we're following R10, and R10 doesn't really do much of category theory. So not much, but we'll see some of it at least. Okay, so yeah, so that's halfway through the proof. We showed that ZA is a subset of S. Then we showed that S is also a subset of ZA. How you do that? You take an element n. For every element n of the subset, it's an integer multiple of A. Right, so yeah, that's what we have to show, that every element of S is an integer multiple of A. That's how to show. Yeah. You try to do this with the Euclidean remainder theorem, if you remember how to do that. It's an elementary number theory, but what you do is essentially you write n is equal to qa plus r. So this is assuming that n is not a multiple of A. So if it's not a multiple of A, it's going to leave some remainder. Let the remainder be R. So n is equal to qa plus some remainder R. And of course, this remainder is going to be less than the A itself, and it has to be positive. Alright. But as we know that ZA is a subset of S, So this QA is an element of S. It is. And since S is a subgroup, yep, S is a subgroup, we know that. So R is equal to N minus QA, right? We just take it to the other side. R is equal to N minus QA. That will be also in the subgroup because of the definition of the subgroup, right? It contains all the it is closure. It satisfies the closure under addition. Yeah. So N minus QA is also in S. So R is in S, QA is in S. So QA plus R, that is N, is also going to be in S. So now by our choice, A is the smallest positive integer in S. Yep. While the remainder R is in the range 0, between 0 and A, the only remainder that can be taken in S is 0, right? Because the thing is, R equals to N minus QA happens to be like something smaller than A, right? That's how we define the remainder. But we know that A is the smallest positive integer in S, so R has to be equal to A. And for that, sorry, wait a second, I messed up. Right. So R has to be less than A, and R is also in S. So that means it has to be 0, right? It cannot be A. But it also has to be in S, and 0 is in S because it's the identity. So R is the identity itself, equals to 0, and N is the integer multiple of, and thus N is an integer multiple of A, that is QA. Okay, that was confusing, but it makes sense. Hello Dan.
Right.
We're doing a lecture on abstract algebra. Feel free to follow. Okay, so we have a couple more propositions until we're done. We'll see some of them, and the proofs, as you can see, are pretty detailed. And it's not that they're like kind of difficult to follow. It's just that like they're very reductive. Okay, any questions? Okay, so now okay, let's see an application for this theorem, right? That we just saw. Okay, so if you have a subgroup, you have subgroups that contain just two integers, A and B, then the set of all integer combinations are A plus SB, so those are like the linear combinations of A and B. So that can be represented as like ZA plus ZB. So essentially, what you're doing is you're having some element RA. So RA is going to be in ZA and SB is going to be in ZB. There are multiples of A and B. Thus you can take the addition for those, and then you get a set with the addition on it, and that will be a subgroup of Z plus, right? And this is a subgroup generated by these two elements A and B because it's the set of all the linear combinations of these two integers A and B, and it is the smallest subgroup that contains both A and B. Yeah. Okay, so if you assume that A and B are not just the identity, so they're like distinct elements, integers, then using the theorem, you can say that this subgroup S has the form of ZD, right, for some positive integer D, and you can see where we're getting at. So it is the set of integers divisible by T, right? So it's going to be like the ZD is going to be here the multiples of D, but D is something that divides both A and B, so it's the GCD of A and B, the greatest common divisor, right? And you denote it as usual by GCD of A and B, and that's an interesting application of this, which is pretty important. I think you'll see this in arithmetic number theory very early on. Yeah. Okay, so we have some proposition regarding this ZD. So let's see. So if we have two integers A and B, they're both non-zero, and D is the GCD of both of those integers. And then this D is going to generate the subgroup S, right? Which is ZA plus ZD. So ZD, which is the again, it was the set of all the multiples of D. Remember, it is also going to be ZA plus ZB, right? So if that's the case, then D divides A and B, right, as I was saying. And if an integer E divides A and B, then it also divides D. There are integers R and S such that, there exists integers R and S such that you can write the GCD in terms of a linear combination of these two integers A and B. And so this is a linear combination like this. Yeah, and part C is just saying that D is an element of S, because we know that S is just this set. So it can be represented in terms of a linear combination. Okay, so now if you try to show A, you can like pretty much conclude this very easily, that if A and B are elements of S, which they are, and S is equal to ZD, of course, then D is like D would be is going to contain both the multiples of A and multiples of B, right? So it's going to divide A and it's going to divide B, and that's what we want. And next, if you have another integer E that divides both A and B, so let's say E divides A, so you can write right, so if E divides A and E divides B, then as we know, A and B are like divisible by D, so that means E has to divide D as well, because E can divide the linear combination of D, that is RA plus SD. Right. Yeah, right. So if E divides A and B, then E must divide any integer of the form MA plus NB, right? Because anything that divides A and B is going to be a linear combination of A and B, right? So that is MA plus NB, and D is one of those. So yeah, C from C you can imply B, but from B you cannot imply C, because here it is like very general. E divides any integer of the form ma plus nb, but it doesn't say anything about the greatest common divisor, right? So D is like a special case of this condition, right? So you cannot imply C from B. Okay. And yeah, there are a few things about the Euclidean algorithm that you can do using this manner. Finding the GCD of these elements repeatedly, and that's called the Euclidean algorithm. And you have a few corollaries from there, and we're going to see those corollaries, and then we'll be done. Okay, so yeah, what are the corollaries? If you have pair of integers, if you have a pair of integers a and b, and they're relatively prime, so they're relatively prime, meaning that they had, like, the GCD between them is 1, right? So the only positive integer that divides both of them is 1, right? So they are relatively prime if and only if their integers aren't as such that you can write Ra plus Sb is equal to 1. So you can write the linear combination of these integers to represent 1. And this is something you can do using Euclidean algorithm repeatedly. But the other way, which is straightforward, is that like Ra plus Sb, you can do that for the GCD of any two integers a and b, right? And as they are prime here, relatively prime, so that means that GCD is 1. So you can write the GCD using linear combination. So you can write it for 1. So the other corollary is that if p is a prime integer, and if p divides a product ab of integers, then either p must divide a or p must divide b. P cannot divide both of them, right? Because then p is going to be like a common divisor for both of them, which is not possible. So we'll see in the proof. We start with contradiction. Let p be a prime which divides a and b. Wait. Suppose that the prime p divides ab, but does not divide a. Okay, it does not divide a. So the only positive divisors of p are 1 and p. That's prime, right? Since p does not divide a, they are relatively prime, right? So the GCD of a and p is 1. Therefore, their integers are not such that you can write the linear combination of a and p equals to 1. Yeah. Then what you do is you multiply this with b. You can write Rab plus SBb is equal to b. Now we know that p divides both Rab and it divides SBb, so it must divide b as well. So that's it shows that if it does not divide a, it must divide b. So it divides either one of those, right? And these kind of proofs are like very common if you do elementary number theory, which I used to do a few years ago. But yeah, and one of the things that you can try to play around with is just how we define the greatest common divisor. You can do the same for the least common multiple, and they do that actually in this proposition, but I don't think they get into much more detail, but yeah. Okay, so yeah, so we're going to see this. This is the last thing, and then we'll be done for today. So yeah, you can have another subgroup of Z plus associated with a pair of integers, namely the intersection of ZA and ZB. So ZA with ZB will give you the common multiples of A and B, right? Now, ZA and ZA intersection ZB is a subgroup. Yeah, that's easy to check. It is not the trivial subgroup. Yep. Because it contains the product AB. Yep. Okay. So ZA intersection ZB has the form ZM for some positive integer m, right? So ZM is going to be so this is kind of confusing. The ZA intersection ZB is a set, and that set contains elements of this form ZM. So there are multiples of some integer m, and this integer is actually the least common multiple of A and B. And as you can see, this is a direct implication from this theorem, right? The smallest positive integer. So the smallest positive integer, m, which is going to give you the form of ZA intersection ZB, will be something that is going to be a common multiple of A and B, and is going to be the least one. So that's how we have the least common multiple, the LCM of A and B. And you have this proposition related to that. So you have two integers A and B. M is their LCM. Yeah, and this is the positive integer that generates the subgroup ZA intersection ZB. Yeah, so ZM is equal to ZA intersection ZB. Yep, and just like GCD, M is now divisible by both A and B because it is a common multiple, right? And if an integer n is divisible by A and B, then it is divisible by m, right? So this is the same language as we use for the GCD. And from this, you can have the corollary, which is like something you learn in middle school, I guess. Which is that you have the GCD of the two integers A and B, that is D, and you have M, which is the LCM of the two integers A and B. Then you have the following law, which is that the product of the integers themselves is equal to the product of the GCD and LCM. So AB is equal to DM, and you can show that in 2 lines actually. What you do is as D is the GCD of A and B, so B over D is going to be an integer because D divides B, right? So B over D is an integer. And A divides AB over D, right? That's because you now have this as a multiple of A. Similarly, B also divides AB over D, right? Because this is also a multiple of B. So now you have something that is divisible by both A and B. So now M must divide AB over D, and it does. So and we know that DM divides AB. DM divides AB. Does it? It does. Right? D divides A and B, and okay. Okay, so DM divides AB. Next, we write D is equal to RA plus SB. That's just the way you can have a linear combination for the GCD. Then you multiply this with M. So DM is equal to RAM plus SBM. So RAM, okay, is something that is divisible by AB, right? It is, because M is a multiple of both A and B, common multiple, right? And the same for SBM. So these two things can be divisible by AB. So DM can be divisible by AB. Thus, DM divides AB and AB divides DM, and they are both positive, and each divides the other. So they have to be equal. So AB is equal to DM, and yeah, that was. And with that, we have completed everything we needed to for today's session. Any questions? No? Okay. So yeah, so we'll meet tomorrow for the PSAT at 3 p.m. UTC. We're going to discuss the problem sets. And on Thursday, we're going to have the next lecture on group theory. We're going to meet cyclic groups and some interesting properties about them. We'll see isomorphisms, and we'll also see homomorphisms, I guess. Yeah. So, yeah, thanks for joining. Hoping to see you tomorrow.
Thanks for the lecture.
Yeah. Okay, have a good day, everyone.